上次都准备好了，然后结果就12点的时候开始。
So what we are going to show now is that any matrix F such that the determinant of F is greater than 0, because we already put that restriction on F, so the determinant of F has to be greater than 0. Now we are going to show that F can be written as a rotation matrix multiplied by the square root of F squared. Or F is equal to the square root of F squared R. And what we're going to show is that these are unique. Now for me to be able to take the positive square root of a matrix, I just want to make sure that this matrix is already positive. Is F transpose F positive or not? This is equivalent to saying -5 squared. Is F transpose F positive or not? Now, we only, in matrices, when we say positive, that only applies to symmetric matrices. So is F transpose F symmetric or not? So, the first problem, so we're going to go through this using a few problems, and the first problem is, we want to show if I have a matrix such that this matrix has the determinant greater than 0, I want to show that these two matrices are positive. By positive, I mean they're symmetric matrices, and their eigenvalues are positive as well. So, now F transpose F, the transpose from the problems that we did in the previous assignment, this will be equal to F transpose F. So, F transpose F is symmetric. Now, is it positive definite? Well, let's see. Pick U in R3. U is not equal to 0. And let's see what happens when I multiply U by F transpose FU. Now what do I know by the matrix F multiplied by U, not F multiplied by U? I know that this is greater than, always greater than, or equal to 0. Because the dot product of two vectors of the same vector by itself is greater than 0. And it's only 0 if FU, if the matrix F multiplied by the vector U is equal to 0. And this is only true if, because the determinant of F is greater than 0, therefore F is is invertible. Therefore, FU is equal to 0 if and only if U is equal to 0. Therefore, if U is not equal to 0, which means U of F transpose FU, so F transpose is positive definite, and similarly we show that F transpose F is also positive definite. So the first part is that we show that if I take F and I square it, but I square it by multiplying F, I get a positive definite symmetric matrix. So what does a positive definite symmetric matrix do with a positive definite symmetric matrix. Remember, a positive definite symmetric matrix, it's a symmetric matrix. I can find a coordinate system in which the matrix is diagonal, not only this, all these diagonal numbers are positive because it's a positive definite symmetric matrix. M1, M2, and M3 are greater than 0. How do I know that they're greater than 0? Because it's positive definite, and we talked about this, and we said that you have to show that in your text you have the proof one way, and you have to know the proof the opposite way. So revise the proof for positive definite symmetric matrices and their eigenvalues. Revise the proof for the statement about positive definite symmetric matrices and their eigenvalues. Okay, so since I have M, and if I choose a coordinate system, if M is a positive definite symmetric matrix, for example, it is equal to F transpose F. It's a positive definite symmetric matrix. I can find a coordinate system in which it's diagonal and the diagonal components are positive. Then I can find a square root by simply taking M1 power half and this M power half is also a positive definite symmetric matrix because I'm taking the positive square roots. This is a positive definite symmetric matrix, and it is equal, if you want to take M and you multiply it by itself, if you take M power half, let's call it U, and you multiply it by itself, you get M. So U multiplied by U will be equal to M. Now, is it unique? Can I find another one? It is unique because this positive square root is unique. You only get one positive square root. But let's maybe assume there are two positive definite symmetric matrices that you can, so assume U1 is a positive definite symmetric matrix, and U1 is equal to F. And assume I have another one, a positive definite symmetric matrix, U2, and U2 is equal to F. Now M is positive definite symmetric matrix. Now what we need to show is that U1 and U2 are the same. Okay, well let's look at the eigenvalues. Eigenvalues and eigenvectors of M, U1, and U2. We're going to use the eigenvalues and eigenvectors to show that they are the same matrices. M, now we know M is positive definite symmetric matrix. It has 3 perpendicular eigenvectors and 3 positive eigenvalues. So M V is equal to lambda 1, M1 V, where M1 is the first eigenvalue. Which means that U1 V is equal to the square root of M1 squared V. And U2 V is equal to the square root of M1 squared V. U1 minus the square root of M1, U1 plus the square root of M1, V is equal to the 0 vector, and U2 minus square root of M1, U2 plus the square root of M1, multiplied by the V, vector V is equal to 0. So this tells me either of I U2 minus square root of M1 I U2 plus square root of M1 I. So this tells me that either, I'm going to put the positive here, and the negative here, the positive here, and the negative here. So this tells me that either square root of M1 is an eigenvalue of negative square root of M1 is an eigenvalue of U1, or positive square root of M1 is an eigenvalue of U1. Now we assume that U1 is positive definite, therefore root M1 is the eigenvalue of U1 and U2. Because I cannot use negative square root of M1 as an eigenvalue of U, because I said U is positive definite symmetric. Not only this, this also shows that this is 0. Also, V is the corresponding eigenvector for both U1 and U2. U1 and U2 are positive definite symmetric matrices. They share the same eigenvalues, they share the same eigenvectors, they are identical. Which means I can only find one positive square root of a positive definite symmetric matrix. Now I can find other square roots, but only one is positive definite. The matrix 4, 0, 0, 0, 4, 0, 0, 0, 4 is equal to one positive definite symmetric matrix squared. But it also has many other matrices not positive definite. Also negative positive, positive negative. If you exchange any of those, all of these are not positive definite, and they are they are symmetric matrices, and they are the square root of this matrix, but they are not positive definite. We only have one that's positive definite and symmetric. So, what have we shown? Let's go back to revise. What is it that we're trying to show? We're trying to show that F is equal to a rotation matrix multiplied by the square root of F transpose F. Now what we showed is that the square root of F transpose F is a positive definite symmetric matrix. It exists, and it's a positive definite symmetric matrix. What we now need to show is that this is a rotation matrix. So, to know whether it's a rotation matrix or not, I'm going to take R, multiply by R transpose, and see what happens. And I'm going to define R. Now F is equal to R, multiplied by the square root of F transpose F. I shouldn't be using the square root in matrices. This is just for illustration. This is equal to R U, and U squared is equal to F transpose F. So what's R? R transpose? R is equal to F U minus 1, which is F transpose F minus half. So R is equal to F U minus 1. R transpose is equal to U negative transpose F transpose. U is a symmetric matrix. U negative 1 is equal to U negative transpose. So this is F U squared negative 1 F transpose. U squared is equal to F transpose F negative 1 F transpose. Now AB negative 1 is equal to B negative 1 A negative 1. And so this is equal to F minus 1 F transpose negative 1 F transpose. So this is equal to R. Therefore, R, can I say it's a rotation matrix or not? What can I say now? So those who are awake. What's that? So, is this statement correct or not? What is more correct at this stage? Yes, it's orthogonal. How do I know whether it's a rotation or not? The determinant. That's right. Let's find the determinant of R. Well, R is equal to F U power negative half. So F, the determinant of F U power negative half. This is the determinant of F, the determinant of U negative half. This is positive, and this is the inverse of a positive definite symmetric matrix. It's also positive, so this is positive. Therefore, the determinant of R is equal to 1. Therefore, R is rotation. So, what we showed is that F is equal to R U, where U is equal, U squared is equal to F transpose F, or you can look at it if you want, R, the square root of F transpose F. And similarly, you can show that it's also equal to a V, which is equal to the square root of F transpose multiplied by a rotation matrix R. Now U and V are unique. We showed that there's only one positive definite symmetric matrix of that is the square root of the positive symmetric matrix F transpose or F transpose F. Therefore, I'm going to put here S. This is a rotation. Therefore, R and S are also unique. So R and S are unique. Is there a relationship between R and S? Yes, R equals S. How would you show that? RU is equal to V multiplied by S. I'm going to put here R S transpose. This is a rotation matrix multiplied by V by S. This is a positive definite symmetric matrix. Therefore, this whole thing, S transpose Vs, is also a positive definite symmetric matrix. Therefore, I can call it, let's say, call it U prime. But we said that this decomposition is unique. Since this decomposition is unique, U is equal to U prime and R is equal to S. Which means that U is equal to R transpose V R. So, let's just go back. What did we prove? From the beginning, we proved that if I have a matrix whose determinant is greater than 0, I can find the rotation matrix in a positive definite symmetric matrix that's equal to the square root of that matrix squared, such that F is equal to RU. Now, why is this important? Because any real strain measure, any good strain measure, should be function of which component, R or U? Should be function of this component, U. Shouldn't be function of R. Any strain measure should only look at the stretch part and should ignore the rotation part. So the reason why this is important, because what I'm interested in is the stretch, because that is what gives me strain. Rotation does not give me any, should not give me any strain. So, we said that F is equal to a rotation matrix multiplied by U. U is a positive definite symmetric matrix, which means I can find a point system in which U is diagonal. I can find a point system in which this matrix is diagonal. And so RQ, this is a rotation, this is a rotation. This is the diagonal matrix lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. This is a Q transpose. Lambda 1 or lambda 3 or these lambdas. are the square root of M1, square root of M2, square root of M3, where M1, M2, and M3 are the eigen values of F transpose F. And this is equal to a rotation matrix P multiplied by this diagonal matrix. Let's put it here. Lambda 1, lambda 2, 3. And this is called the singular value decomposition of the deformation gradient. I can find those three matrices, a rotation matrix Q transpose, a rotation matrix P, and the three, and a diagonal matrix with lambda 1, lambda 2, lambda 3 that describe my deformation. And for elastic materials, as we will see later, all the constitutive laws for elastic materials are given in terms of lambda 1, lambda 2, lambda 3, which are the principal stretches of the material. These are called the principal stretches of the deformation. And this is called the singular value decomposition, and it's also used in many different applications. You might have heard of it if you've done any numerical techniques, any courses on numerical techniques, because it's used in many other applications. Okay, so these are, you have an example in your book in which, given any matrix with the determinant of F is greater than 0, you can try to do it by hand. To do it by hand, you need to find F transpose at F, find the eigenvalues and the eigenvectors. So find Q, the diagonal matrix Q transpose, take the square roots, so U squared, which is equal to F transpose F, and then U will be equal to Q, and the square roots, so that's the procedure. If you're going to do it by hand, is as follows. You've got F transpose F. This is a positive definite symmetric matrix, so this is equal to Q multiplied by a diagonal matrix that has M1, 0, 0, 0, M2, 0, 0, 0, M3, multiplied by another rotation matrix. This is equal to U squared. U will be equal to Q transpose Q, square root of M1, 0, 0, 0, square root of M2, 0, 0, 0, square root of M3. So this is your U, and R, U negative 1 is equal to Q transpose Q 1 over root M1, 1 over root M2, 1 over root M3, and then you can find R as equal to F U minus 1. So this is if you're going to do it by hand, but the software also has, and you can look at the example, look at code, find the decomposition. So this matrix that has those numbers can be decomposed into, this is a rotation matrix P, this is another rotation matrix Q, and this is a diagonal matrix, and these numbers are the square roots of M1, square root of M2, square root of M3, where M1, M2, M3 are eigenvalues of F transpose F. Okay, Okay, so far, we did touch on the strain measure, just the small strain measure. And then we talked about the deformation gradient, the decomposition of the deformation gradient into rotation and stretch. Now, we need to talk about the strain measures that are actually used in any solid mechanics problem. Before we talk about the strain measures in a three-dimensional case, we are going to talk about the strain measures in a uniaxial case. And you need to realize two things. That your strain measure should be local. What do I mean by local? It should not, for example, if you have a bar with length L0, and finally, after you pull it, it has a length L. If you say the strain is equal to delta over L0, this is not local. This is an average. Why is it an average? Because if you look locally on this element, if this, for example, bar is made out of a non-homogeneous material, where on the right it's soft, on the left it's stiffer, so you might find that the strain here is 100%, and maybe the strain here is 0. So the strain measure should be local. It should tell me the strain at a point rather than the strain overall. Also, the strain should consider rotations. So if this bar is rotating in space, I need to be very careful what delta I'm measuring. Am I measuring this delta? Am I measuring this delta? Or am I measuring, which delta am I measuring? Because if I'm measuring this delta divided by L, it's different from if I measure this extension in the bar. If it's rotating, I have to be careful what I'm measuring. So these have to be taken into consideration whenever I'm performing a three-dimensional analysis of strain. So we're first going to start by introducing uniaxial strain measures. Now the strain measure depends on how you want to measure it. And the one that they were used to is the engineering longitudinal strain on average. So first, if I have a bar of length L0, and I pull this bar, now it becomes with a length L, and I'm going to call delta is equal to L minus L0, and the stretch is equal to L over L0, and this stretch is the same stretch that appears here. Lambda is equal to L over L0. The engineering longitudinal strain is equal to delta over L0, L minus L0 over L0, which is equal to lambda minus 1. The true strain is defined as length L over L0, which is equal to length lambda. The green strain, absolute green, is defined as half L squared minus L0 squared divided by L0 squared which is equal to half lambda squared minus 1. When lambda is almost equal to 1, I have a very small deformation. You'll find that absolute 3 is equal to half lambda minus 1 lambda plus 1. This will take the 2, which will equal to epsilon small and will also be equal to close to the logarithmic string, or what we call the true string. So they're all equal at small strings. This is lambda. Well, lambda is close to around 1 or around 1. When lambda is around 1, the strain at 1 for everything should be equal to 0. When the stretch is 1, the strain should be equal to 0. And they're all give you the same strain at small strains, but they deviate from each other as the stretch gets bigger. The three-dimensional strain tensors, the function of the three-dimensional strain tensors is to do the following. If I have an object and I have a vector drawn on the object that describes a direction on that object, the function of the strain matrix is to do the following. This is dx. The function of the strain matrix is when I multiply epsilon, which is the strain matrix, by dx, I get what is equivalent to delta. It's the delta but in vectors. It's the three-dimensional vector that gives me, in a uniaxial case, it gives me delta. In a three-dimensional case, it gives me a vector that corresponds to how this new vector has changed. And to find the strain along a vector, what I need is the orthogonal projection. What's the orthogonal projection? This is epsilon dx dot dx. I can put the dot product anywhere. And if I want the strain, I need to divide by the x-axis. This is what the function of the strain of a matrix, the strain matrix. This is what the function of the strain matrix is. So we're going to just define the strain matrices that we use. The first strain matrix that we use, which is the small strain tensor, E is small, and we defined it already. It's equal to half the gradient of U plus the gradient of U transpose. And we talked about the different components in that strain matrix. So what about this strain matrix? Now the first thing is this matrix. If I change the coordinate system, it abides by the rule that in the new coordinate system, E prime is equal to Q EQ transpose. And we know that partial U1 by partial X1, which is the diagonal component, the first diagonal component, is almost equal to delta over L naught, the direction of E1. And so on. Partial U2 by partial X2 is equal to the delta over L naught in the direction of E2. And then, so this is equal. This is epsilon 1, 1. Epsilon 1, 2, which is equal to negative half partial U1 by partial X2 plus partial U2 by partial X1. This gives me gamma 1, 2 over 2, which is engineering shear strain divided by 2 in the plane E1, E2. I have any other vector dx, then the strain delta over L naught along the vector dx can be obtained by simply taking dx dot epsilon dx divided by norm dx norm dx. So this is delta over L, but in the direction of the unit vector dx. Now, if I have a vector dx and a vector dy, and between them there is an angle theta, then after deformation, if this vector becomes dx and this vector becomes dy, and the angle between them is theta, then the straight matrix tells me something about how the angles change in space, because half dx dot dy minus dx dot dy divided by norm dx norm dy is equal to dx dot epsilon dy divided by norm dx norm dy. So given the vector dx and dy, I can know how the dot product change, which for small deformations will be equal to cosine small theta minus cosine capital theta divided by 2. So for small deformations, the lengths we assume stay the same. The length of capital dx stays the same after deformation. The length of capital dy stays the same. So you end up with just the cosine of the ends. Now the strain is symmetric. What does it mean that the strain is symmetric? There is a coordinate system in which the strain is diagonal. So just an example to explain why the strain depends on the coordinate system. Imagine this object with 90 degrees, and you push it here such that it now has this shape, with exaggeration of course. If you look at a cube here, or a small cube inside the material, this is the original shape, and this is the final shape. No shear strain. Why no shear strain? Because this angle is still 90. So in this coordinate system, the strain matrix is diagonal. If I look at this the other coordinate system, if this is the original cube, fix one side will look more like this. And so there is not that. So there is shear strain. So it really depends on how you look at which coordinate system you're looking at. So atom small is used in, now of course I'm pulling this out of a hat, but I'm not exaggerating. I don't think I'm exaggerating when I say it's used in 99% of the simulations concerned with traditional engineering materials. Whenever you're dealing with beams, you're using those partial U1 by partial X1, partial U1 by partial X2, you're using these components of the engineering or the strain matrix. The definition of the strain is according to this matrix. However, as we showed earlier, what will happen if I have a motion that's described by rotation? Let's say x is equal to cube x, where q is equal to cosine theta, negative sine theta, or positive sine theta, negative sine theta, cosine theta, 0, 0, 1, 0, 0. I have an object that's rotating. U is equal to x minus cube x. X minus x, which is equal to q capital X minus x, q minus I multiplied by x, the gradient of u is equal to q minus I. This is a matrix, partially u I by partially xj. So this is equal to cosine theta minus 1, sine theta 0, negative sine theta, cosine theta minus 1, 0. The small strain matrix is equal to have the gradient of u plus the gradient of u transpose, cosine theta minus 1, sine theta minus 1, 0, 0, 0, 0. So what does this tell me? As an object is rotating, if theta is small, I will predict very small strain. When theta is very close to 0, the numbers are going to be actually very close to 0. But once an object starts rotating with large deformations, you're going to start to see very large values of the strain, which will actually, if you're doing any large analysis, any analysis with large deformations, this will give you some errors, and that's why this matrix cannot be used if you're doing some sort of analysis, for example, finite element analysis, or any sort of analysis where you end up with an object that deforms, where this element has a very large rotation. For example, this is 45 degrees. Then the results will be wrong, because you're going to predict additional strains inside that element only due to rotation, not due to anything else. Also, if you're trying to buckle some sort of an object, buckling includes rotation, because buckling basically means that this element prefers to have this orientation, where it's oriented at a different angle. If that strain measure is used, you're punishing the material for buckling, for rotating, by saying that you need stresses for it to buckle. You need additional stresses, fictitious stresses for it to buckle. And that's why for buckling, you have to use large analysis or large deformations. So for that 1%, where you actually require large deformations, where you want to model buckling or anything with large deformations, you cannot use this strain measure. A better strain measure is the green Lagrangian strain tensor. The green Lagrangian strain tensor is defined as half the gradient of u plus the gradient of u transpose plus an additional term. And this takes care of that rotation. For example, if the gradient of u is equal to q minus I, just a rotation matrix, just similar to the problem that we talked about earlier. The gradient of u is equal to q minus I. You'll find that epsilon green will be equal to half q minus y plus q transpose minus I plus q transpose minus I q minus I. This will be equal to half q plus q transpose minus 2I plus q transpose q minus q transpose plus I, which will be equal to the zero matrix. In fact, epsilon green is actually equal to the volume. Half F transpose F minus I. If you know that F is equal to, we said x is equal to x, u is equal to x minus x, the gradient of u is equal to F minus I. So F is equal to I plus the gradient of u. So epsilon green is in fact equal to F transpose F minus I, which is equal to half u squared minus I. So the green strain tensor, let's now revisit the deformation gradient. The green strain tensor is a function of this F transpose F. It's function of the positive definite part of the deformation. It's only function of the stretch, and it does not consider the rotation. Everything else applies to epsilon green. Everything that we talked about for the small matrix applies here, with a slight addition is that when I take this is vector dx, dx dot epsilon green dx divided by norm dx. Norm dx gives me the engineering, the green strain along dx. Previous matrix gave me the engineering strain along dx. This gives me the green strain along dx, which is equal to half L squared minus L naught squared divided by L naught squared. And to see this, the green strain is equal to half the new length, which is dx dot dx, minus the original length, which is dx dot dx divided by L squared, L naught squared, which is norm dx, norm dx. Now d small dx is equal to half this is f dx, this is f dx, so dx dot f transpose f dx minus dx dot dx divided by norm dx, norm dx. Because of the linearity of the dot product, I can take dx as a common factor, and because of the linearity, I'm going to take that number, half, and put everything here. Which is basically what we just defined as our green stream matrix. And this applies if I, instead of dx dot dx, I put half dx dot dy minus d capital X dot capital dy divided by norm dx norm dy. This is also equal to dx dot epsilon green dy divided by norm dx norm dy. There are many other strain tensors that you will find used throughout. Strain is according to how you define it. Some other strain measures are the logarithm of the different components of U, and this is called the Henke strain. A nominal, there is another strain measure called the nominal strain, which is equal to U minus I. The green strain that we just introduced is equal to half f transpose f minus I, which is equal to half U squared minus I. Any general strain matrix, strain tensor, can have the form 1 over m U power m minus I. So according to your application, you might see any of those strain measures. A good strain measure, you know right away if it's function of U or function of, so we said F is equal to RU, which is equal to VR. You know that it's a good strain measure if it's only looking at the stretch part and not the rotation part of the deformation grid. So you have a lot of problems in your textbook. I would recommend that you look at all these problems. They're simple, they're more on the undergrad level, but just take a look at them for, because it gives you, they're more numerical problems, so you can get a measure of how to use those strain measures. All right, so we'll give you 5 minutes.
You need to